Okay. We're gonna move on to chapter 11. I got some. I'm hoping I have some.
I thought we were just playing.
You prayed. Yeah, you ditched my party.
I didn't ditch you. I didn't say I was going.
Yeah, you did.
No, I said I might be able to go.
He did.
And that was the night.
Over what? A smorgasbord?
No, my parents were like, we have food. And so I went upstairs and it was like a large. But I didn't know that more people. I probably would have come.
I'm always paying for the games after school. You know that.
Right now my college classes haven't started, so I'm free.
Kramer, after closure now.
Well, if I try to have it at a random time, you don't show up.
Hey, hello. And I've played more and well since so it's like a
So why don't you like after
not
school?
showing up to his party.
Because he wants to go home. That's why you don't like after school.
Because you're easy.
No, I already blanked school.
Joking.
Why after school? Okay. So we're gonna talk. This is where we're really kind of separating from. We're separating from the motion stuff. We're still doing motion, but it's different types. It's wave motion. So we're not gonna do any of those kinematics equations anymore. We're gonna be doing waves, sound, all the fun stuff like that. Mirrors, light. Yeah. Refraction, reflection, all sorts of fun stuff like that. Why you can see light when the sun's past the horizon.
Wow,
And I'm thinking about making you guys read a book, reading a couple chapters in a book and writing a paper on it.
Yes.
Origins. How old are you?
Have you ever heard of the what's it called? The principle. I can't remember the principle now. The principle where like everything's so perfectly fine-tuned.
Your original complexity.
Utopia!
What's it called? The part where like if you mess with any of the physics constants in the universe, life couldn't exist.
That is actually irreducible complexity.
No, it's not called.
Butterfly
Not even smart. Actually.
Okay. Anyways, so this semester is gonna be fun. Gonna have some Goldberg stuff going on. I've already had Cole come in about 15 times to ask me questions about the project, so it'll be great.
Hey, we came once. We were gonna lever down.
Okay. So we're gonna talk about repeated motion. Okay, so we're gonna be dealing with this whole chapter is really dealing with simple harmonic motion. Sounds bad, but it's not so bad. Okay? And simple harmonic motion is a repeated motion, a repeated pattern. Can you think of any motion that is repeated back and forth, back and forth?
A pendulum.
A pendulum. A pendulum. The
Saving
Newtonian
thousands of
law.
dollars on scholarships.
A cartwheel.
A cartwheel.
Let you go back and forth.
All those
That would be very hard to do.
All those boomerangs on Instagram.
Oh, that's
Those are so annoying.
Oh, yeah.
Okay. How about an acrobat swinging on a trapeze?
What about
Playground swing.
when it first like Steven?
A seesaw.
Yeah, but we continue to go back and forth, back and forth, back and
on a
forth.
trampoline.
Wait, the seesaw work?
Trampoline, metronome. You
Yeah.
music people. Isn't that a music thing?
Oh, yeah, sure. That's
Yeah,
No, Crane's just not a music thing.
it seems very useless.
Okay.
Yeah.
I agree. I've never really understood.
Veronica Harris.
Okay. So, one type of periodic motion, you're going to think this is silly, but it still works. Okay, one type of periodic motion is a mass attached to a spring. Okay, you pull the spring, you let it go, And assuming ideal conditions, what would happen?
It'll launch.
It would go on forever. Now we know under real conditions it wouldn't go on forever because of what?
Friction.
Friction.
I totally
Air resistance.
There's also friction.
That's fine.
It's like staring at me.
The image drop.
Okay, now it says, I mean, if you think this semester is going to be easy, you're wrong. The direction of force acting on the mass is always going to be opposite the direction of the mass's displacement. That's really wordy. All that's simply stating is the force applied is opposite the displacement from equilibrium. Make sense?
Is that the third part
Hmm?
of Hope's song?
No, I haven't even given you Hooke's law yet.
Oh, so what did you just say?
I just said this, which simply says that when you're dealing with periodic motion or simple harmonic motion, the force is always going to be opposite your displacement from equilibrium.
Okay.
So this is equilibrium, right, where the spring is not stretched or compressed, correct? Okay, so technically there's no displacement, so therefore there has to be no force. Right? If it's a non-stretched or a non-compressed spring, are you going to have a force at that point? No. Okay? But if I take it and I stretch it, the spring is pulling that direction, correct?
Yes.
Okay? And my displacement from equilibrium is that direction. Everybody see it? Versus if I take and I compress it, okay, my spring's pushing that way, correct? That makes sense. Okay? But my displacement from equilibrium is the opposite direction.
Yes.
Okay? That's going to become important because Hooke's law has a negative in it to account for the opposites. Okay?
Oh, wait. Didn't we have the spring force constant earlier?
That was like kinetic energy of the spring. Like,
Yeah.
Yeah.
Okay.
It might be exactly the same thing.
No, there's no force or negative in them.
The spring is.
No.
Well,
No, I'm
once
saying
it's.
it
Was-
It's like
wasn't
I
it
know that
KX
the spring
squared?
is-
It was K squared is no square.
Yeah.
So it's the force.
0.8.
No, it's like after you let go, then the spring is.
No.
Okay, so you have your spring.
What, do you want me to go back to the slide? Okay, so now this is something you're going to need to know, and you're going to need to know well. This slide, I don't know if you need to make an asterisk or a star or highlight it or whatever. This is pretty important for your being able to understand periodic motion or simple harmonic motion. It's that there's always going to be an equilibrium point. An equilibrium is when you have what? Tell me what equilibrium means. No acceleration, and also then if you don't have acceleration, you can't have a what?
Force.
No force, right?
Yeah.
No net force means no acceleration, correct?
Yes.
And I showed you in that previous slide, there were the three pictures. The middle one was the one where it was at equilibrium, right?
Yes.
It was not compressed, it was not stretched, so therefore you have no net force and no acceleration. Okay? Okay? The spring force and the mass's acceleration are always going to be zero at equilibrium. Now notice it says the speed reaches a maximum at this point. Now, the only time it wouldn't be at a maximum would be under what situation?
Not an equilibrium. Has not like repeated? Or no?
Kind of. The only time where you're not going to have a maximum speed at equilibrium is if you set it at rest at equilibrium.
Nice.
Does that make sense?
Oh, that's
But,
stupid.
yeah, that's kind of a stupid question. But I was just trying to make sure that some of you probably be like, how is that possible? Well, let me just show you what I mean. Like if this is showing this to show that it's moving. Does that make sense? But if you remove that and we were just sitting there at equilibrium, you wouldn't have a maximum speed, would you? Okay? But if I pull it and let it go, I'm going to have a force all the way until I hit equilibrium. Well, a force is going to cause an acceleration. An acceleration is going to cause you to speed up. So therefore, when you hit equilibrium, you should be theoretically going the maximum speed. Until you go past equilibrium, where you will slow down. Right? So if I let go, it's going to speed up, speed up, speed up. And then as soon as I get past equilibrium, now it's going to slow down, slow down, slow down. Speed up, speed up, speed up, maximum. Slow down, slow down, slow down. Speed up, speed up, speed up, maximum. Do you see what I'm saying? want you to process that a little bit.
No, I got it.
Is it because when the spring what do you call it?
Compress?
Yeah, compresses, that's when the slowdown is. And they'll speed up as it shoots.
Yeah, well, it depends on the direction. Like, as it's going this way, it's compressing, so the force is opposing the motion, so it's slowing down.
Yeah.
But then it'll eventually turn around and start going this way, which will be going with the motion. It'll be speeding
Okay,
up.
so the bottom one will speed up towards the right, and then as it comes back, it'll.
It would be slowing down if it was going left, and it'd be speeding up if it was going right.
Okay.
Yep. Okay. And so, if I go back to this main slide here then, this speed reaching a maximum at equilibrium should make sense. Right? Okay? Then it says that maximum displacement. That would be the farthest right you could get, or the farthest left you could get, or the most compressed or the most stretched. Does that make sense? When you're at the most compressed or the most stretched, you should have a force that is at a maximum, right? The most compressed would mean you have a very strong force due to that compression. Okay? And therefore, your acceleration should be at a maximum. Here's what's interesting. The speed is what?
0.
So how can you be accelerating
Change the
when you don't have...
Crane.
Who would have thought there was so much acceleration when you're not even...
Who would have thought inertia is a cool
That's not even
Right?
I don't think it's not.
So if you can put the kind of the model in your brain when you're going through this, I think this makes sense. But if you don't think about what's actually happening, you just look at this, might common sense tell you that
That is not true.
that's not right.
That
Okay?
is not true.
So remember to think about you can have acceleration even though you are not even moving.
That's pretty lame.
That's pretty sick.
Okay, so all this says. Measurements show the spring force, and I will use spring force and restoring force as they're the same. The spring force is the force that it would need to restore itself back to equilibrium. Does that make sense?
Yeah.
No? One person?
What is the force back to equilibrium?
Right, the spring force is always going to be the force that causes it to come back to equilibrium or restore itself back to equilibrium. So when I say spring force and restoring force, I'm referring to the same thing.
But won't it make it go past equilibrium?
Yeah, only because of momentum and inertia. Right?
That's what this drawing did, so I was just talking about it in the third one. So it goes one direction, and then it's moving in the opposite direction. Would it not always be equilibrium?
I'm not 100% sure. I'm not sure it's that simple, but you might be onto something with that. Okay, so here's your equation. Do I have it? Did I give it to you?
Would you suggest keeping the old note card and writing more stuff or making a new note card? Do we need the old one anymore?
I would.
I'm not throwing it away.
I would be okay starting a new note card, but there are some things that you're going to have to definitely remember, like weight or gravity is mg, stuff like that you might still need to use. Okay, because we're going to use Fg equals mg this today. So,
But thank you.
okay.
Just ask me.
Now, notice how it says the force of the spring is directly proportional to how much it's been displaced. That should make sense. The more you displace it, the stronger the force is going to get, right?
Correct.
Okay? The further away from equilibrium, the stronger force your spring is going to be applied because you've got to either strongly compressed or strongly stretched. Okay? I think I talked about K with the spring, or was that a different class? Did I pass around springs?
Yes.
Yes.
It's different than every.
Okay. Okay, so really what K tells you is how stiff the spring is. And I'm pretty sure I remember passing around different springs, and one was stiffer than the other.
How do you measure how stiff?
Feel it.
Good question.
Is a bigger number?
I'm sure there's some sort of computer program that they can apply figuring out how much force. What did you say?
Is a bigger constant more stiff?
I'm pretty sure.
Okay.
Because it would take more force to So again, here's where that negative comes in, or I said earlier, the negative's in this equation because your force and your displacement are opposites of each other.
Wait, is it always the same value in the opposite?
Same values.
Like, how's that different?
They're proportional, they may not be the exact same number. So they change proportionally, like if 1 is 2 and 1 is 4, as they change into 4 and 8 or something like that. Okay, do I want to do this? No, I think I want to do this process.
Hey, Crane,
Anything else? Yes?
is the negative just to make sure that you don't have a weird force?
Is a what?
Like, what's the purpose of the negative?
To keep it so that you're dealing with more positive numbers. However, you still got to take into account like negative direction stuff, which we'll get into as we finish probably.
Right after I get home, I get goldfish and hot coffee or
I get a
tea.
box of Cheerios.
Go
If
sit
you
in my
didn't have the
bed.
negative, if you didn't have the negative, you would assume that they would both be positive, or they would both be negative, a proportional relationship.
Hold it.
But, can you have a negative direction but a positive force?
Yes, that's why that negative's in there, because they're opposites. Because if I, for example, if I put in a negative x, that other negative will cancel out to give you a positive force. That make sense? Let me
Is it
show you.
because the spring constant is always positive?
So like, if I have f is kx, and that's negative, and I have a negative displacement, and I put in negative 0.2,
I see.
these two negatives make sure that that is going to be a positive force.
There's always opposites.
Yeah, these are always opposites. Okay,
These problems are pretty easy.
relatively.
Right, hold on. It's two variables.
You say relatively, that doesn't tell me yes or no.
Okay.
You know, relative to.
Okay. So let's do this problem here. We got 8 minutes. You got 2 problems here. So if a mass of 0.55 kilograms is attached to a vertical spring, stretches the spring to 2 centimeters from its original equilibrium position, what is the spring constant?
Derek, do you? Oh, what is that? High quality.
That is a great spring. Yeah.
It's like a broken.
That's the equilibrium.
Is a spring a screw?
What?
No, it's not.
If there was a thing through it,
Oh,
It's
or
not.
if it was wrapped around, like if you could.
That's pretty good too, isn't it?
It's a string.
If you put little rings on
Okay,
it.
the box now. Okay, so from here to here is our 2 centimeters.
Why is that?
What is that? Why?
Here to here is our slanted.
Cranes, I think you should do things on purpose to help with people's OCD.
And help our
That's just
focus.
incorrect. I said that.
We see something and we hop right
What?
there.
I said that.
Okay?
Those look like butterflies.
Now, we have to think about this situation here. If we're at this position, we're going to kind of assume here that we're at the maximum stretch and it's just hanging there.
Stretch.
Everyone just.
Just sounds for her. She's all excited.
I just realized lunch is next.
Alright.
Remember, no self-harm. If you can't do it, then I
I'm
can't do
focusing.
Okay, where was I going with this? Okay, so I can do a free body diagram of this little box here, right?
it. How does the...
We had a spring force, that's which direction?
South. Oh, wait, yes. Yep. It's up. You're good.
Say FE because it's an elastic. Okay, and then we got what else going on here?
Downward force of gravity.
Yummy.
And no
Now, in the context of this problem, those two forces should be what?
Equal.
Equal to each other.
Wait, so are we assuming there's no friction?
Wait.
No, it's resting there. It's resting there.
It's just,
So they're-
Oh,
it's not bouncing, it just, I put a spring, hung it, and let it hang to a certain point. Okay, so our F net is 0, should equal F, is FK is friction? FE. E plus FG. Would you agree with that?
Oh, so we can find the elastic by the...
So since it's Fn.
Right?
So is this the one where it was like Fn?
I know I'm not accelerating here, which means I have no net force in this situation. So if I do a free body diagram, my forces should equal out to give me 0.
Yes.
These are my two forces.
Wait,
But
Let's plug in the equation. Isn't this negative kx?
Yes.
And this is a negative force, so I'm going to go negative mg.
That'll work.
What?
Because
Gravity is mass times g.
Okay, so
Maybe you need to keep your note card from last
Okay,
night.
what about
Gross.
Warm your
Great.
hands by the fire.
I wasn't referring to you specifically, that's not all of you.
Wow.
Stop! You guys make things way worse than they actually.
That's so gross.
It's okay, because it's just
Hey, that's harm.
Okay? Any questions on this?
Hey, how about we take it once, but then do negative
Fe,
Yeah.
this is the force of, this is a spring force.
So is that the 0?
No.
Oh, I understand.
Here's my free body diagram.
That's a slurp.
Never mind. Gotcha. Yes.
So I'm replacing the spring force with what it equals. Okay? Do I need to show the equations up?
Is that another equation you can use? FE?
No, this is just using the idea of equilibrium. Okay? So now I can take and I can bring the kx over here. And so I can solve, right?
Amen.
What do I want to solve for?
MG.
Okay.
I want to solve for k. Where's what?
Oh, no, where did MG come from?
I look forward
There's
to
gravity going on here.
You can't hear it.
Oh,
Okay? In this situation, I'm at equilibrium, or I have a net force of 0 here. Would you agree with that statement? If I take a spring, have a box attached to it, let it hang, just sit there. Okay? What forces are acting on it? The spring pulling up, gravity pulling down. They must be equal if it's not moving, right? Okay, so they'd have to be 0 if you add them together. Equal and opposite? Okay? So if I add the spring force and the gravitational force together, I should get 0. Right? So now I'm just plugging in the equations. Fe is negative kx. Fg is mg, but we know that this is going to be negative force because it's downward.
Oh, okay.
Does that make sense?
Just kind of chilling out.
I'm taking mg, plugging it in, that's where I got this. I'm taking this, plugging it in for Fe, that's where I got this.
He's just replacing that with
Substitute. Okay? Then I'm just solving the problem.
this one's right here.
Okay, sounds
Okay? We know M, don't we?
Yep.
We know G, right?
Yep.
What's X?
Or is it point?
It's negative. Oh!
Displacement, got it.
Oh yeah, because it's opposite the force.
It's negative because it's downward.
It's going down.
Cranes up some brothers.
Wait, I thought the force was going.
Wait, so.
Yeah,
Gravity.
It's a negative times
This is the spring force.
No, the force
Right here,
is-
Steve. Spring force is up.
Oh,
It's
okay.
opposite.
Yeah, I got it.
It's
So,
the.
We're doing.
Negative 0.55 kilograms.
That's what cranes does.
Times negative
We're gonna have to do negative 9.1.
or positive.
9.81. Our X is negative. That's why the negatives cancel.
What if we find the negative with
Calm down, please.
Oh,
I needed to convert that to meters. So all I did was make it so hard.
Oh my word.
Great, that's the hardest thing.
I'm still gonna.
Yeah, you are gonna.
What are you struggling with?
I was so confused.
No way, you did it.
What'd you do?
I didn't. No, I didn't point.
Cold.
I'm not saying my mistakes have not taught me misery enough.
Wait.
Oh, it isn't.
You guys know why this is a newton divided by a meter?
Because
This should be a meter per second squared, and a kilogram times a meter per second squared is a newton.
Oh!
he's like from the equation.
Also, because that's a force divided by a meter.
Yeah.
So your spring constant's pretty stiff.
Stiff boy. Stiff.
That is the word of
That's a stiff boy.
Stiff.
Yeah,